Welcome back to another video of Math Times School. In this video, I will be doing the second. So let's read it. I can prove that the segment joining the midpoints of two sides of a triangle are both parallel to and half the length of the third side of a triangle. So we're given that these are midpoints, right? And then let's just name this any value, right? Let's name it, let's say x. Both of these sides x, and these sides y. So we have to prove, number one, that this triangle right here, and then we have this triangle. So the big triangle. We have to prove that this length is half of that length, and that this length is parallel. So let's begin. So as we can tell, that they both share an angle, and so they would be congruent. So this angle would be congruent to itself, reflexive property, and then so we have this. So we know that this length is x. We know that this length is 2x, right? Because x plus x is 2x. We know that this length is y. Whoops. So that this would. Why isn't my marker working? Okay, let me see if this works now. Okay, so we know that this is y. Sorry, we know that is y, and that this is 2y, right? And then now we can prove that these two triangles are similar by side because we know that, see, 2y divided by y is equal to 2, and then 2x divided by x is equal to 2, and then so we know that they are being dilated by 2, so that two sides are proportionate and one angle is congruent. Now we know that these angles are similar. Okay, so we can now prove that this length is half of this length because this triangle is created by this triangle dilated by 2. Okay, and then we have to prove that this line is parallel to that line. Okay, let's see. So we know that when two triangles are similar, all angles are congruent, right? So we know that this angle, these two angles are congruent to these two angles. Let's make that 3. So we know this. And then now we know that we can prove that these two lines are parallel because corresponding angles of parallel lines are congruent. So since their corresponding angles are congruent, they are parallel. And you would usually get a question like this. Like let's do one problem that's like that. So let's say you were given two triangles, right? Let's say this triangle and then that triangle. Actually, yeah, this triangle and a triangle in between. So let's say you're told that these two lines are parallel, right? You're told that this length is 4, and this length is, 4. And you're told that this length is 3. And you're told to find just this length. So this is how we would solve a problem like that. So you'd have your first triangle, that, and then your bigger triangle. Okay, so we know that this is 4, and that the whole length is 8. Actually, before you even do that, we have to prove that these two triangles are similar. So we know, oops, oh my god. Okay, so we first have to prove that these two triangles are similar. So again, we know that they're parallel, and so we know that these angles are congruent, right? We only need 2 angles to show that these two triangles are congruent. And so we have angle, right? And then bang, we've proven that they're similar. Now we can move on. So we can see that this length is 4, right? 4. And then this whole length is 8 because this is 8. And then we know that one angle, we can also say that this angle is congruent to, so I'm just going to add that, right? Anyway, we didn't need to show that, okay. And then we know that this is 3, so what could x be, right? We proved that they're similar, and so we can just do it like this. We can set up like a ratio, so x over 3. So x divided by 3 is equal to 8 over 4, right? and then 8 divided by 4 is 2, times 3 is 6, right? It doesn't really matter what number is the denominator and which is the numerator. So if you had it like this, you just have 3 is equal to 4 over 8x times, this would be, you can just simplify that to 1/2 and then multiply by 2. You get x equals 6. So as long as both corresponding sides, or at least the sides of the same triangle, are at the same place. So they both have to be at the denominator or maybe numerator in this example. Okay. Let me quickly look at the study guide. So okay. So let's actually do a few more So I can perform and identify dilations of lines and line segments. So let's say you had a line. I'm sure I went over this in my similarity basics video, but I'll go over it again. So let's say I had this line, right? Actually. So let's say you had this line, right? And this length was 4. Actually, I don't really know. Okay, let's say this was 1, 1, and this was 2, 0. It wouldn't look like that, but let's just say it was that. We had to dilate this line by 2. Center point being at D. Because we always have to have a center point, because if we don't know the center point, then you don't really know where to dilate. So since the center point is D, since it's a line, it would continue on the line. If the center point was here, it would continue that way. Okay, so let's say we're dilating it by 2, and so we have to go the distance again. So let's say this length is 1, right? I mean, it is 1, right? The length is 1. So when we dilate it by 2, the next length has to be 1, so it's 3, 0. We can also oops, not 3, 0. Yes, okay. Okay, so we could do it like that, right? Or we can just add by the rate of change. We can just add by the rate of change, so you can see that the y changes by what, like -1, and 1. So it's this would be it. So I know it doesn't look like, actually, why not just do this way? Yeah, I should just probably do like this. Let me just. Am I allowed to rotate this? Yes. Okay. Yeah. Okay. This is a bad drawing. Yeah. Let's just to make this a bit simpler. Okay. I don't want to confuse you guys, so let's just do like this. So 1, 1, 0, and next point being 2, or 2 is a 1, 1, and next point being 2, 0. Right. C 1. Actually, no. Wait a minute. Was it? Okay. Let's just do 2, 1. Yeah, okay, 2, 1. Well, okay. My examples are so bad. Okay, let me just. Oh my god. Okay, wait. Let's just keep it like this. Who cares? Okay. 1. Okay. I don't know. Let's say distance is. Okay, no. Let's just do it like that. Okay, sorry about this. So it's just. So we have it like this. So this is 2, 2, 1. Whoops, 2, 1. Okay, so we're dilating it by 2. So we can just get the rate of change, which is 0. over 1. This would go out to 0, but we're not done yet. So when we dilate, we're just going to add this to the previous point, or we could just multiply this by 2. I'll show you what I mean. So let's say the dilation factor is 2, right? We can just multiply the top by 2 and the bottom by 2, and we get 0 over 2, right? And we can just add these values to the original point. So 1, 1, right? 0, that's 2. Added is 3, 1, and as you can see, that is it. That is this point. So this point is 3, 1. Yeah. Okay. 3, 1. Or we could have just done it like this. We know that this is 1 and it's dilated by 2, so the distance will be 1 greater, and yeah. So we could just say it's 3, 1. So it just continues on the line. So I think this is just the easiest option. So you can see that it goes up 1 and then across 0. And then so it would continue going like that. And since the dilation by 2, you can just multiply the rate of change by the denominator and the numerator by 2. So 0 times 2, because it originally changes 0 on the y-axis and then 1 on the x. Yeah. That seems about it. Yeah. If I were to make this diagram actually accurate, I have to make it like that. Yeah, sorry about the inaccurate diagrams. Thank you for watching this video, and goodbye.